Hello guys, I hope you are doing well. So today we are gonna talk about some physics and our topic will be the wave-particle duality. So let's start first about talking about particles and how they work. So first of all, when describing the movement of a particle, we need to specify its momentum. This allows us, in the simplest cases of course, to determine the equations of motions. So how this works is we just use the famous second law of Newton. We know the basic form that we usually use is m times the acceleration is equal to the forces applied to a particle, but the basic form or the original form is the derivative of the momentum is equal to F. Using the fact that P is equal to m times v, we get, assuming that the mass is constant, dmv by dt equals m dv by dt, which is equal to F, and this gives us the equations of motion as we know in the basics of mechanics. Second of all, we have waves. Properties of waves are specified by their frequency f or their wavelength. These two quantities are uh, two two aspects of one concept, and depending on these properties, the behavior of waves varies. One famous characteristic of waves is diffraction. This is true for mechanical waves as well as electromagnetic waves. So if we take a laser here, and we have here a little split, and if the wavelength of the beam coming from the laser is in the order or smaller than uh, let's say in the order of the split here, we're gonna see this figure instead of just 1 point as you may think, and this is known as the diffraction. So now moving to light, and here starts the wave particle duality. For several years, light was considered as a wave. This was first stated by Christian Huygens and was confirmed later by Thomas Young by the famous double slit experiment. So if we take light for example, and this is no, at first we didn't know it was a wave. So if we take some light source and we take here a wall where we have two slits here, so we see in if we take a screen here, we see that the light takes this shape here, and this is the intensity of light. In the center it is very concentrated, and it gets weaker and weaker in the edges and when we get away from the center. So this is the same as the diffraction that we talked about here. So by this time we knew that light was a wave, and later by the theory uh, of Maxwell, we build up stronger theories of electromagnetic waves, etc., that supported this theory. In the beginning of the 20th century, some experiments suggested that light was made of particles, and this was confirmed by Albert Einstein in the famous explanation of the photoelectric effect, and later Arthur Compton in his Compton effect. So we said that light was a wave at first, but then some experiments suggested that light was a particle as well. Uh, we have two famous experiments, or the first one is the photoelectric effect. If we take here a metal, for example, and we make we take some beams of light with uh, a known frequency and wavelength, etc., we notice that some electrons left the metal plaque, and this suggested that light was made of particles, and these particles kick off electrons from the metal and they move away. This was uh, what was suggested by by Arthur Compton and the Compton effect when he took an electron at rest and he took an incident photon. So when the photon hits the electron, we notice that the electron recoils from one direction and the photon recoils or scatters from another direction with another frequency and momentum. Here it was P equals h nu over c, and here it's P prime equals h nu prime over c, where h is Planck's constant, nu is the frequency, and c is the speed of light. So these experiments suggested that light was made of particles, and these particles are called photons. So light was in the same time waves and in the same time particles. So after centuries of debates whether light was a wave or a particle, it turned out that it was more than that. It was both at the same time. And this both at the same time. And this discovery rewarded both Albert Einstein and Arthur Compton their Nobel Prizes, respectively, in 1921 and 1927. I guess some of you think that Albert Einstein got rewarded the Nobel Prize for his theory of relativity, but unfortunately it was not, and he didn't get Nobel for this discovery. So now, mathematically, light is a wave that has a wavelength and a particle that has momentum, and they are related to each other by the formula P equals h over nu. So if we know the wavelength, we can deduce the momentum. So this equation reunites both aspects of light, uh, the wave aspects, which is defined or characterized by lambda, and the particle aspects, which is defined by p. And things get interesting from this point. Sorry, there is an S missing here. So at first, light was considered as a wave characterized by its wavelength lambda. Some hundreds of years later, it turned out to be made of particles too, which we call photons, and these particles have momentum p equals h over nu. And we know that everything around us is made of particles, so can we reverse our reasoning and say that particles are waves? So at first we said we have waves, and then we found out that waves are actually particles as well. So we want to do the opposite. If we take particles, are they waves? If we take, for example, electrons, atoms, molecules, human beings, are they waves as well? So here comes one of the most ingenious things I personally saw, and that looks really easy, but it rewarded its owner another Nobel Prize. So our guest will be Louis de Broglie. So he's a French physicist, as you may notice from the name. So what de Broglie was doing is taking P equals h divided by nu and writing divided by lambda, sorry, and writing it lambda equals h divided by p. So just take lambda here and p there. So this is what he did, and this was called de Broglie wavelength and awarded him a Nobel Prize in 1929. So the physics behind this is that if we take a particle of momentum p, it has a wavelength lambda, and if we do the double slit experiment, for example, for slits, sorry, there is no e here, that have the size in the order of lambda, we will see diffraction, and then we would see that wave nature of particles. So as the same way that waves do scatter or do diffract from double slits, we can do the same experiment, for example, to electrons and determine their wave and observe their wave behavior. And this was confirmed by Davisson-Germer experiment. So in this experiment, we took a crystal. So here is a crystal which is made of atoms. So each dot here is an atom. There is 1, 2, 3, 4, etc. So instead of taking just 2 slits, we have here a lot of them. And if we take an incident beam of electrons, the electrons will scatter and come here as an intense reflected beam. And as we said before, if we take a screen here, in the center it is very strong and it gets weaker and weaker as we get away from the center. So this was the the wave particle duality in a nutshell. I hope you understood. I hope it was entertaining, and see you in the next time. Thank you so much.